Dear students, welcome back. So, in continuation to the wave and oscillations that we had started. So, in the previous class, we had seen for the undamped oscillations, that is also called the free oscillations. So, when we had given the mass to a spring, and when the spring is oscillating along with the mass, then it will have a certain frequency, and that is called your angular frequency, and we can represent that angular frequency by omega or omega naught. So that frequency with which the spring is oscillating, that is called your natural frequency. So with the you are not giving any input, external input or internal input in that oscillations, then that is called your natural oscillations. Now we are going a little beyond that, right? Also we have seen when the oscillations is taking place, it is in the nature of the sinusoidal wave, and we had from there we had continued and we had seen how you have got the concept of the phase. That is how the phase is coming when a wave is propagating, right? That is what we can say, that the moment a wave has started, at the starting point itself it has both the sine and cosine components with a different value of the amplitude. That is, the magnitude of the amplitude may be different, and those magnitude are going to superimpose in the space, right? And that after superposition they are creating a resultant amplitude. So that we had called the individual amplitude as C plus D, and when they have combined together, then we had got the resultant amplitude, and that we had called A. So A was equal to under root C square plus D square, and between C and D there was a phase, and from there we had got the constant of the phase, and therefore we had written the wave as the displacement of that wave is equal to x equal to a sine omega t plus phi or a cos omega t plus phi, and this is how the concept of the phase has been introduced. So phase is the imparted in the motion itself. It is not any external things which has come from somewhere else, right? Now today we are going to look into the damped oscillations. That is, if the same thing is going to oscillate into a medium under which the oscillations, the amplitude of the oscillation is going to change. So what can be the change? So naturally it cannot increase, it will only decrease, right? There is a case in which the amplitude can increase also, that will do separately, but today I'm going to look into how the amplitude can decrease, and if the amplitude can decrease, then what will be the differential wave equation for that, that is differential equation for that, and how we can solve that differential equation to in the mathematical form to convert this into a sinusoidal wave. So this is primarily we are going to look into in today's class. So before I'm going to look into the damped oscillations, first let us have a small review on what are the different type of the oscillations. So there are three main types of the simple harmonic motions. The first one is called the free oscillations, about which we have so far we have understood. That is a simple harmonic motion with a constant amplitude and the period and no external influences. That is the spring with the mass is oscillating freely. That is, let us suppose here you have got any support. Under this support here you have one spring, and here you have put any mass, right? And if this mass is going to oscillate up and down freely under any you don't have any external resource, that is, it is frictionless. Let us suppose here spring constant is k, but this is under vacuum, let us suppose. So if it is going to oscillate under the vacuum, its amplitude is going to be constant, and in that case the angular frequency that we are you get, that is called your omega naught, and that is called your natural frequency, and this is what we have already seen in the previous class, right? So example of your free oscillations, here you can see the spring is coming up and down here in this case. So here a spring is going up and down from the mean position, right? And a wave is getting generated. So this is your wave which has got generated over here. So as you can see, it is coming in a sine or cosine wave. So this is the, you can say, the ink mark which is being put on the paper, and if this paper is going to move, then what will happen? This wave will also be moving, right? So this type of the simple harmonic motion is called free oscillations, and it is oscillating without any influence, right, with its natural frequency. Now we are coming to the damped oscillations. So simple harmonic motion. So it is also a simple harmonic motion, but decreasing amplitude and varying period due to external or internal damping forces. Now, for example, let us suppose you have a pendulum, and pendulum naturally is swinging in air. So air is going to give you the resistive force. This is the simplest example that I'm giving you, right? So here the air will have the resistive force. Under the resistive force, it is going to oscillate, and that type of the oscillations will be called as the damped oscillation. See this diagram here. So here you have the spring. This spring is going to oscillate. This spring is oscillating, right? And then a wave is being generated. So this is the amplitude of the wave that is going to be generated. And as you can see in this, the amplitude is going to decrease. So as let us see here, this is your first amplitude and this is your second amplitude. Now you see it has decreased. So what is happening here in this case, the amplitude is going on decreasing way, and this type of the oscillations will be called as damped oscillation. So today we are going to write down the differential equation for this damped oscillations. And the third one is forced oscillation. So what is the forced oscillation? A simple harmonic motion, but driven externally. So what you are going to do here in this case, it is driven externally. It does mean you are going to apply some external force along with this. So as you can see over here, this is a swing, and to maintain this amplitude or even to increase this amplitude, one person is standing over here and this person is pushing that swing, and this amplitude will remain constant. Even he can increase the amplitude. So naturally here you are going to give the two type of the angular motion. One with the swing. So this girl is swinging, so it will have a particular frequency. So natural frequency, let us suppose that is your omega naught. And this person who is standing, he is also giving from outside, and let us suppose that frequency that he is providing is your omega, right? So in this case, this amplitude, natural frequency can increase, and the natural frequency is going to increase. Accordingly, your amplitude can increase or decrease. So this type of the motion will be called your or oscillations will be called your forced oscillation. So now I am going to start with your free oscillations with its differential equation. Now let us start the damped oscillation. So let's see the introduction of this damped oscillation. If the total mechanical energy of oscillating system are conserved, right, the system would oscillate indefinitely with the same amplitude. That is, if a pendulum is going to oscillate in a vacuum, then pendulum will never stop. It will indefinitely it is going to oscillate with its frequency, right? So then what I'm saying is amplitude is going to be conserved lifelong, right? However, in real situation, however, there are always non-conservative forces such as friction or drag forces present. That is, if this spring is going to oscillate, or the simple pendulum is going to oscillate into the air medium, so air will become your drag, and that is going to reduce the amplitude. These dissipative forces decrease the system's total mechanical energy and can be either internal or external to the system. So the force which is capable of decreasing your amplitude can be both internal or external. So naturally the energy which can change the amplitude can be both the internal or external. The amplitude will gradually decrease and oscillation will die out. So slowly it is going to decrease, and there will come a time when oscillations can even stop. That is, you will have your completely zero oscillations. The amplitude will die down. And oscillations which dies away is an example of the transient motion. So this is also called the transient motion. Example include the pendulum with the damping forces, with which all of you are aware. Now here you see one of the example. Let us suppose here, as you can see here, you have got the spring system, and this spring system is attached with the mass m. This is your mass m with which it is attached, and let us suppose this spring is going to oscillate. So here, if it is going to oscillate, it is going to oscillate with its natural frequency, and let us suppose its natural frequency, angular frequency we are talking, is your omega naught. Now let us suppose here I have kept a viscous liquid. So here there is a liquid, right, in which this mass has been submerged. The mass has been submerged inside the viscous liquid. then this liquid is going to put the viscous force on this mass, and under this viscous force, the amplitude of this oscillations will decrease, right? Because this liquid is going to put the resistive force on this mass, and moment the resistive force is coming, the amplitude is going to decrease. So naturally, this is one of the example of your damping oscillation. So an example of the damped harmonic oscillation is shown in the figure. It is like a simple harmonic oscillator, but now the mass is immersed in a viscous fluid. When object moves through the viscous fluid, it experiences a frictional force, and frictional force, this forces dampens the motion, right? All right. Higher the velocity, greater with the frictional force. What is the velocity? The velocity with which this mass is going to do up and down. So in 1 minute, how many times it is going to put up and down? Let us suppose if it is going to 50 times in a minute, so then you will have a particular velocity. If it is taking 100 times per minute, then it will have a different velocity. So more be the velocity with which it is going to oscillate, more will be the frictional force which will be acting on this, right? The damping force on the mass in the figure is proportional to its velocity. So now more be the velocity, more will be the damping force. So here approximately you can say it is directly proportional. However, it is not always directly proportional. For example, and in case of the airplane, frictional force is proportional to the square of the velocity. Frictional force is square of the velocity because the aeroplane is traveling at a very high speed, right? So there the damping force which is acting on the aeroplane will be the square of the velocity, right? Now if you are going to increase further velocity, you can have the supersonic or ultrasonic the aircraft. In those cases your frictional force will even more, which will see these cases in the shock wave, right? So what I'm telling over here, if the velocity is comfortably less, then the frictional force is directly proportional to the velocity. However, this is not a universal law. So here the differential equation that I am going to derive is, we are going to take there that the frictional force or your viscous force is directly proportional to your velocity. So let us look into and let us derive the differential equation, find out the differential equation and try to solve it, right? So differential equation for the damped oscillations. So this is the figure, the same figure we are going to continue. That is, here you have the spring system, this is your spring system, and this spring system is going to oscillate into this viscous fluid in which it is going to oscillate, and this viscous fluid is going to put a resistive force. Let us suppose the resistive force or viscous coefficient or proportionality constant is your B, because what you say, the viscous force F is directly proportional to the velocity. So F is directly proportional to V, and proportionality constant I am calling as B, right? So B will be your proportionality constant. Under this concept I am going to derive this equation. So let us suppose a spring is attached with the load of mass M, and it is freely oscillating with the velocity V in the fluid of the viscous coefficient B. Viscous coefficient of the fluid is B, as shown in the figure. The viscous force acting can be given as F equal to minus B into V. So it is just like your frictional force, which always act against the motion. So F equal to minus B into V, where B is your frictional force or the viscous force here you can say, because it is acting in the fluid, and V is the velocity with which the mass is taking up and down inside this fluid. So what will be the differential equation? Now here again we have to apply the Hooke's law. Now you see, we have already seen, firstly you apply on this spring system, right? This spring system. So what is this? On this spring system we had calculated m d square x upon dt square is equal to minus k into x. If you remember, in case of the free oscillations that we have done, what was the equation? M d square x upon dt square minus k upon k into x is was equal to 0, or m d square x upon dt square is equal to minus kx, right? Then what I had done, I had divided both sides by m. So this m I had divided. So what was the equation? D square x upon dt square is equal to minus k by m into x, and k by m we have called as omega naught square. right? So this is what we had taken. So this part that I have circled it over here is your free oscillations. Now a damping force is acting, so naturally it is acting against the motion, so here this has been subtracted. So minus b, and v is equal to y dx upon dt, because here is your v is the velocity, v is equal to dx upon dt, where x is your displacement. So x is the displacement up to which it is while it is moving, right, up and down, up and down. So from the mean position it is going to stretch or contracted by the value of x. So I hope you must have understood this. So what I'm saying, what will be the differential equation for this? M d square x upon dt square minus kx minus b dx upon dt. B minus b dx upon dt has come because of the viscous force. Now all those things you take on the left hand side. So what I can say, m d square x upon dt square plus kx plus b dx upon dt is equal to 0. Now what do? You divide all the terms by m. All the terms by m. So this is going to be d square x upon dt square plus k by m into x plus b by m into dx upon dt is equal to 0. Now you remember k by m was called your angular frequency, or omega naught square. And b by m, here I am going to introduce another constant. Naturally b is your viscous coefficient and m is the mass which is attached on the spring. So these are again constant. So b by m is equal to, I am saying, 2 omega, and k upon m is the same angular frequency, omega naught square. So this is what I am going to say again here. K by m is equal to omega naught square, as we have seen in case of your free oscillations, and b by m is equal to 2 gamma. B by m is equal to 2 gamma. This is another constant that I have introduced. So whenever we have written b by m, we can take 2 gamma, or if I have to convert back gamma into b by m, then what we have to do, the moment we are getting 2 gamma, I can convert it back into b by m. That you should always remember, right? So I am going to substitute this value here. So k, for the k by m, let us suppose this is your equation number a. So for the k by m, I am going to put omega naught square, and b by m I am going to put 2 gamma. So your equations comes out to be d square x upon dt square plus omega naught square x plus 2 gamma dx upon dt is equal to 0. This is your first equation. Now this is your differential equation. What we call, this is your differential equation for your damped oscillation. So what is the difference? Only one term has been added. What has been added? 2 gamma dx upon dt, where 2 gamma is nothing, b by m dx upon dt. This term has been added in this. So naturally solution will also change. So now I am going to solve this equation. So this equation I have already solved in case of the free oscillations, but now I am going to by taking this a sine omega t or a cos omega t, whatever, we can take anything. But here I am going to solve with respect to the complex form of the wave. We can solve in any way, because you have already seen in the phasor representation and the complex representation how the sine wave can be written in the form of the complex form, and the complex form can be written to the sine or cosine form. So now, so solution of the differential equation for damped oscillation. Now let us see. This is the equation that we have seen in the previous slide, that d square x upon dt square plus omega naught square x plus 2 gamma dx upon dt is equal to 0, where x is the displacement, right? That is the value with which the spring is getting stretched or contracted, right? Now this is the second order differential equation, right? This is your second order differential equation, and the general solution of this can be given as x equal to a e to power alpha t. You can also write x equal to a sine kx minus omega t, or a e to power I omega t minus kx. Whatever you wish you can write, but now you see in this form, right? X equal to a e to power alpha t. So what I require to do, the general solution of this, the value of the x can be given as a e to power alpha t, because you have already understood when it is oscillating you will have a sinusoidal wave, right? So you can write x equal to a e to power I omega t, or a e to power I minus kx omega t, all those things, or x equal to a sine omega t plus phi, or x equal to a cos omega t plus phi. All those things you can write. Same thing here, I have written x equal to a e to power alpha t is also the same thing. It is representing you sine or cosine wave. Right. Now what I require to do, here you have d square x upon dt square. Here, right, here the first part you have d square x upon dt square. Here you have dx upon dt, right, and here you have only the x. So x you already have. This is the general solution because it's a sine wave, right? Now if I'm going to differentiate this 2 times, I can get dx square x upon dt square, right? If I'm going to differentiate 1 times, I will be getting the dx upon dt, and x you already have. So all those things I'm going to do and substitute in equation number 1. So let's do it. So after differentiating once, dx upon dt equal to, what I can say, a is anyway constant, and here you have the alpha. So what I can say, a alpha e to power alpha t. Again you differentiate, what I can say, a alpha square e to power alpha t. So these are your second derivative, and this is your first derivative. So substitute this value in your equation number 1, and what you are getting. So what I have done, just I have substituted the value d square x upon dt square a alpha square e to power alpha t. You see here I have substituted. Then omega naught square, right? X equal to how much? A e to power. So here I have forgotten to write. You should write it here. Here x equal to a e to power alpha t. So you write here a e to power alpha t, a e to power alpha t. So that is there, plus 2 gamma, and dx upon dt. This is your second derivative here. This is your second derivative. That again here I have written, right? A e to power alpha, a e to power alpha t I have written. So now what I am finding, a e to power alpha t is common in all, because here also you have, right? So a e to power alpha t is common in all. So what I can say, this is your alpha square plus omega naught square plus 2 gamma alpha, and this value is coming out to be equal to 0, right? So a e to power alpha t plus alpha square into alpha square plus omega naught square plus 2 gamma alpha is equal to 0, right? Now what we can say in this equation, either a e to power alpha t is equal to 0, or a square omega naught square 2 gamma alpha is equal to 0. But a e to power alpha t cannot be 0, because this is a general equation. What I know, x equal to a e to power alpha t. So a e to power alpha t that we are seeing over here cannot be 0. So then what can be the 0? To make this equation consistent, alpha square plus omega naught square plus 2 gamma alpha will equal to 0. So this is what I have written over here. So therefore what I am saying, alpha square plus omega naught square plus 2 gamma alpha is equal to 0, right? So let's proceed further. Now you see it carefully. This is your quadratic equation, right? Here this is your quadratic equation. What is the quadratic equation? What should we form? Ax square plus bx plus c is equal to 0. Now this will be your ax square. This will be your ax square, where a is equal to 1, ax square. This will be your bx. This will be your bx, and this will be equal to your c. So this you are getting, what you are getting, ax square plus bx plus c is equal to 0. So this is a form of quadratic equation. So what I can find out? I can find out what is the value of x. That is here in this case it is in form of the alpha. The quadratic equation is in the form of alpha. So what will be the value of the alpha? So minus b plus minus root under b square minus 4ac upon 2a. So minus b is equal to your minus 2 gamma. This is your b. As you can see here, you see this is your coefficient b. So b is equal to your 2 gamma. So I have written 2 gamma plus minus b square. So 2 gamma whole square. So 4 gamma square minus 4ac. So here a is equal to your 1, right? C is equal to your omega naught square. So 4 omega naught square upon 2a, a is equal to 1. So again upon 2. So what I can do, here you have the 4. Here also you have the 4. You take it out of the square bracket. That is the square root. It will become 2. So this 2 here, this has also become 2, this has also become 2, and this will be your 2. All of them will get cancelled. So how much you are getting? Minus gamma plus minus gamma square minus omega naught square. So what you are getting? Alpha is equal to minus gamma plus minus under root gamma square minus omega naught square. This is the value of alpha you are getting. So what you are getting here, the alpha will have the two value. One will have minus gamma plus under root gamma square minus omega naught square, and the another value will be minus gamma minus gamma square minus omega naught square, right? So let's substitute this value in your equation number 2. Where is your equation number 2? Here you see, here you have equation number 2. So let me highlight this. So here you have got the equation number 2 here. This is your equation number 2 here. Okay, not coming. Yeah, here. This is your equation number 2. So substitute this value of the alpha, right? So if I'm going to substitute this value of the alpha, then it will we will have two value. One is gamma plus gamma square under root gamma square minus omega naught square, and another is minus gamma minus gamma square under root gamma square minus omega naught square. So naturally here, this A, as I have already explained you, A is the superposition of the two amplitude, and that is given by C and D. So what I can write, x equal to C exponential minus gamma plus gamma square minus omega naught square into T. This value. One we have taken the plus value, plus D into minus gamma minus under root gamma square minus omega naught square into T. So where A is equal to under root C square plus D square, that I have already shown you in case of the phasor relationship. So here A has been broken, as you can see, into your sine and cosine wave. One is giving you the sine wave and the is giving you cosine wave. So amplitude of the sine wave is C, amplitude of the cosine wave is D, right? And these two are going to combine to give you the amplitude A. So this is what this equation is going to represent. So this is going to be the solution for this, which we require to solve little further. Now here, let us suppose gamma square minus omega naught square, right, equal to, now what I have done here, I have reversed the sign. So gamma naught square minus omega square I am taking. Now here you see gamma naught square minus omega square. So what I have done here, this I have made plus and this I have made minus. So it does mean I have to multiply it by minus. I can multiply this by minus, and I square is equal to minus 1, right? So under root I will equal to your I. So what I can write, I under root omega naught square minus gamma square, right? So I hope you must have understood. So what I have taken over here, let me delete this so that you can again see this. So what I am taking over here, gamma square minus omega naught square is equal to I under root gamma naught omega naught square minus gamma square. So if you are going to reverse your sign, that is minus to plus and plus to minus, then you have to multiply I square, since it is under root. So if I square is coming out of the under root, it is becoming your I, and this value I am saying omega naught square minus gamma square is equal to omega. Omega naught square minus gamma square is equal to your omega, and omega is going to your resultant angular frequency, right? Omega naught is your natural frequency. Omega naught square was your natural frequency, as you had seen. Now what I am saying, omega naught square minus gamma square is your change frequency, and that I am calling as omega, right? So what I am saying, gamma square minus omega naught square is equal to I omega. This value I require to substitute in equation number 3 and solve this equation number 3. And let us see which form it takes, right? So what I have written, x equal to C exponential minus gamma. Here for this I have written I omega, and again here I have written I omega into T. Just I have substituted this value of, that is gamma square minus omega naught square is equal to I omega, right? This is what I have taken in this case. So let's proceed further, right? Let's solve this. So this is the equation that we have seen in the previous slide. Now here you see exponential minus gamma into T, exponential minus gamma into T, because here you have got the T, so it is multiplied, and here also exponential gamma T is there, so exponential gamma T I have taken common, right? So what is left? C exponential I omega t. This is left, C exponential I omega t plus D exponential I minus I omega t, right? So this is what is left out. So e power minus gamma t, and this is your Euler formula, e power I theta, e power I theta. And that if you remember from the phasor complex relationship I had shown you there, it is given by cos omega t plus I sin omega t. So e power I omega t cos omega t plus I sin omega t, and similarly e power minus I omega t, what I write, what can I write, cos omega t minus I sin omega t, right? So now what I have done over here is cos omega t I have taken first common. So now here you see cos omega t. If I am going to take cos omega t is common, then here you have the C, and here also you have cos omega t. Here you see, here also you have cos omega t. So the coefficient of is D. So cos omega t if I am going to take common, so what you have, C plus D. And then here you have I sin omega t, and here also you have I sin omega t. So if I am going to take I sin omega t common, then what I am getting, C minus D. Alright, let us suppose this I am going to say, this is your equation number 5. Now let us suppose C plus D equal to A sin phi. And this again I have shown you in case of the phasor relationship how it comes. C plus D equal to A sin phi. And C minus D, I C minus D equal to A cos phi. Because you go back there and you see there it was C minus D equal to minus A cos phi. There you can go, still you can see there. So this is what I have done here. C plus D equal to A sin phi, and I C minus D is equal to A cos phi, right? So C plus D value in equation 5 I am going to substitute, and C minus D value again I am going to substitute in equation number 5. So substitute the value of C plus D and C minus D in your equation number 5. Then what we are getting, e power minus I omega t equal to A sin phi into cos omega t, because what I have done, C plus D, instead of C plus D I have taken A sin phi, and similarly here you have A cos phi into sin omega t, because for C minus D I have written A cos phi. Now what I am getting over here, now A of course is common. This is your sin A into cos B plus cos A into sin B. So this is your sin A plus B. So A e power minus gamma t sin omega t plus phi. This is the solution for this equation. So what will be the equation for the displacement? Therefore, that was your solution for your differential equation in case of your damped oscillations, and that differential equation should be remembered. Now, in the next class, we are going to take up the different types of the damped oscillations and some of the applications of the damped oscillations. Damped applications have very injuring applications, many number of the injuring applications which you experience in case of your daily life also. To keep your excitement, let me tell you one small example, that when you are moving in your car and suddenly some speed breaker comes, right? So your car is going to come over your speed breaker, right? So it is going to oscillate, but it does not remain oscillating. It will just go up, right? And slowly it will come back, right? So what is there? You have the shocker, and the shocker is going to absorb the oscillations, right? So in the car you have the shocker at all the four wheels, and that shocker is going to absorb the oscillations. So how does that shocker is going to absorb all the oscillations, and how it give you the comfort of the ride in your car? That is one of the applications of your damped oscillations. Not only this, damped oscillations have many electronic as well as your mechanical applications. So some of the applications will be look into, but firstly we have to understand what will be the different types of the damped oscillations, and once we have finished the damped oscillations, then we'll be moving to the forced oscillation. Thank you very much for this class, right? Bye bye.